Hi everyone, my name is Christopher Johann Clarke, and these are my co-authors for the paper Computationally Efficient Physics Approximating Neural Networks for Highly Nonlinear Maps. This is the table of contents, and this is what I'll be going through for the presentation. To start the presentation, I would like to preface the use of the term nonlinearity, as it refers to the property of linearity of a system that adheres to additivity or homogeneity, or does not adhere to, which is opposed to function nonlinearity. So given some function f for all I, we look at problems that present themselves in this form, where function f takes in an input of feature analysis big F of an input x of I and returns you y of I. We can write that function compositionally as f compose feature analysis f that takes an input x of I and returns you y of I. Not all input variables can be collected, right? Because your data collector might not have the proper uh, tools to capture all types of data. So you get hidden variables. And because of certain interactions, we can't always predict all of them. So we will definitely have hidden states. So we have hidden variables h1 to hk and hidden states s1 to sm. Since each h and s will cause the function f to alter slightly, the function f can be represented as carrying or containing a family of functions curly f at the bottom. And in this curly f function family, we have a bunch of functions that map one hidden variable to another hidden variable under the condition of one of the hidden parameters. So we can look at this it's like a toy problem. So given a system, you can see over here that uh, your function f takes in an input x of n and has some hidden parameters and hidden states and hidden variables. Uh, it's a piecewise function that comprises of some adjustment terms, alpha, beta, and gamma, and then we can then impose on it that the adjustment terms are controlled by a set of functions a, b, and c. Now, this a, b, and c will carry memory, and this memory is denoted as n star. So if we assert what we um, constructed just now as the family of functions over this problem, we can uh, define the relationship between the hidden parameters and variables. So at each time step of n, we receive some input from the system, and the input of the system is then passed to the family of functions f, and all of the different hidden variables will then be um, computed by the system and return us the family of functions f results that collapse to the functions a, b, and c, which will then be um, used to adjust the terms for alpha, beta, and gamma, which will then be used to adjust the terms in the piecewise function above. Sorry. And in this case, you can think of it as at each time step, some linear piecewise function is changing slightly, right? So for the topic of physics approximating neural networks, if we construct a neural network taking a positive integer L for layers and number of neurons per layer P, we can construct a function h to look like this, where it takes the form of a neural network, and if we write it as a function composition with a shorthand operator, we can then define it as such. Now we want this h compose neural network function to map to or be as close as, which by that I mean it outputs a y of hat that is very, very close to the actual y that we get from our input of x. So we call this mapping M, and this mapping M is achieved As the error of the network approaches zero, uh, that means that the mapping M approaches our ground truth. So we can also for this topic of physics approximating neural networks, we will construct an approximation layer F and embed this layer within the network. And I'll show more details about that later. But we'll call this approximation layer F star. And to give an example, if we had this function g of x that has these different variables r and t, we can then use the different uh, inputs from our latent inputs from our network. So that's the gamma of x, which is the weight of x plus bias, and substitute that into the original g of x to get what we see on screen, g star of x. Now, if you want to look at it graphically, it'll look like that, with the approximation layer being embedded in between a pre-processing and post-processing layer. And this pre-processing and post-processing layer in our paper, the pre-processing layer was 2 layers by 8 neurons, and the post-processing layer was 5 by 8 neurons. So in the capacitor model, we have this model, which is by van der Veen and van Manen. And since there is finite stiffness and acting damping constant, the plates are always non-uniform, because in a film capacitor, you have two plates that are acting against each other all the time. So this gives us a possibility of a multitude of constants, K1 and K2. And not only that, maybe we have some other interactions going on, right? Like the forces between F1, the two plates, or the mass of at different points of the mesh of the plates, right? So we can think of it as one big interaction tensor. And we can say that the capacitor function C collapses interaction tensor T to return the voltage across the capacitor, which is what we want. But in actuality, there might be some other interactions within this interaction tensor. So we can say the family of function takes in the interaction tensor at each time step of memory and returns as a y after some summation. Um, but in this case, because we're constructing a physics approximating neural network, we will construct the neural network as such, with f star being of this form below, which is each of the variables of the model that were not an input. So all of them are replaced with a latent input variable. Now onto the results. We used this Fraunhofer IDMT SMT guitar dataset, and we distorted the signal of it because previous studies showed a distorted guitar signal, sorry, a distorted signal produced more capacitor nonlinearities. And so a file of about 2E7 samples was used to train the model with the 80-20 split. We used this wave shaper algorithm, and we recorded the output of the system and the input of the system at 44.1 kilohertz with an universal audio Apollo. We measured the high pass frequency, and it was around 9 hertz, so that's far below the region of interest. Our results show that the model performed very well. We compared it to a linear model in blue over here, and a dense model of the same size as the physics approximating neural network of 8 by 8, and they were all trained for 500 epochs at 1000 batch size using the Ada-Grad optimizer. This plot shows you the 10,000 samples and the comparison of absolute error. Now the linear model has almost 3 times higher peak error at 0.08 absolute delta volts, while the dense model has almost 2 times higher peak error at 0.06 absolute delta volts. This also shows that we can transpose it to real time pretty easily. It's a modified dense layer. And so we could also seek further improvement of the model through model discovery using genetic algorithms or network architecture optimizers. And also the methodology displayed shows possibilities of the physics approximating neural network, ultimately achieving more accuracy with the same computational resources. This also encourages the use of informed or empirical models, such as um, mathematical models or mathematical physical models. The This is very similar to the physics-informed neural networks. Thank you very much for listening to my presentation. Please contact me at the email on the screen for any further questions.